All right. Well, I guess we're ready, almost ready to go.
We
It's
are.
almost
Yes.
7.
What's
Almost
up, my
7.
brothers?
Almost the top of the hour. How are we doing there, folks?
I'm doing
Beauty.
wonderful.
Excellent, excellent. Well, we had, I think tonight's registration was about 180 something or other. So
Nice.
this will be fun. Excellent, guy. I see a lot of you folks here already. Jean-Luc has already chimed in. Richard, Martin, how we doing? Very good. Excellent, excellent. I really appreciate this. Is just this has been this. I think this has officially become a thing. Wouldn't you guys agree?
Officially.
I think this is officially a thing now. It's a thing.
It's
What
the Wednesday night thing. Yeah.
It's a Wednesday night thing. It's a happening thing, or a thing that's happening.
It's a get your motor running.
Get your motor running, right? It's 7 o'clock, and you know what it means? It's 7 o'clock, and I want to rock.
I want to get a belly full of beer.
Right. And your sister looks
Never
cute
mind
in
about your
britches and
sister,
boots.
okay?
Yeah. Right. Hey, good evening, everybody. Welcome, welcome, welcome back to Takeo After Dark on this beautiful mid to late October Wednesday evening. So welcome back. Whoops, hold on a second. There we go. This is part 4 of the fall edition of Takeo After Dark. We've already gone through heat loss. We've gone through pipe sizing and stuff like that. We went through pumping away last week and a few other things. Tonight, we're going to start the process of circulator selection. And we're going to go through a few things here. We're going to talk about different types of circulators. And it's not just a matter of, give me one that I can use all the time. Your choice of circulator matters more than you think. The circulator and we don't say that just because we build them. But there's a very compelling case that can be made that the circulator may in fact have more to say about overall system-wide efficiency than either the boiler or the heat emitters. Now there's a provocative statement right there. It might in fact have more to say about the overall system efficiency than either the boiler or the circulator. And I'll note. Rick, go ahead.
The boiler or
the heat emitter. What did I say?
Okay.
Did I say the boiler? The circulator.
Yeah.
Okay. Well, that's because it's Wednesday night and my mind has already checked out. It has more to do with the overall system-wide efficiency than either the boiler or the heat emitter. Thank you. Yes, there we go. So that makes a lot more sense, does it not?
He's just checking on us. He's making sure we're watching. So.
That yeah, I'll go with that.
Oh,
that
he knows I stopped listening to him years ago.
Right. Okay, well, let's get started tonight. We're going to explain that and see what you think. And I'd like you to meet tonight's cast of characters. And if you're kind of getting a gander of my T-shirt, it's one of our. If you were a kid in the '70s, this was like one of the highlights of your Saturday mornings if you watched the ABC cartoons, which was Schoolhouse Rock. And there was just some memorable stuff on Schoolhouse Rock. And we were singing a little bit of it earlier before we started, but Schoolhouse Rock really did rock. So our cast of characters tonight, of course, as Schoolhouse Rocky, that's John, the big muscle-bound guy. Then there's Bill, better known as Dave. And then the conjunction junction engineer, way down at the end there's Rick. So the Schoolhouse Rockers are ready to rock for you. Now, again, a lot of you guys have been here already. If you are a first timer, just bear with. If you're a first timer, pay attention. If you've been with us a lot, bear with us. That little control panel on the right-hand side, make sure that arrow, if the arrow is pointing to the left, click on it and it'll expand the control panel so you'll be able to see what's going on. And again, once it's expanded, then you have your audio section so you can make sure your speakers are working, your headset, whatever. Most of you guys can hear us okay, so please chime in if you can hear us. And if there are any handouts to download, you can see them in that section as well. And then down at the bottom, that's the important one. That's where you type in your questions to all of us. So if you guys just type in a hi, hello, how are you? And that way we know we can keep on moving. Joey, you see colors. Excellent. That's good, I think.
Oh, whoa.
Okay, there we
and if
go.
you're on your device or tablet, things will look a little bit different. It's usually a toolbar across the bottom of the screen, and it just has little icons of the presentation, the cameras, and your question section will be there if you see that. So you can't see it all at one time. You got to jump between the others, but it all works that way.
Very good, very good. All righty. So let's get this show on the road, shall we? And there's my man, Schoolhouse Rocky. All righty. Last week we left off, we talked about a bunch of different things. We talked about the universal hydronics formula, which we use to find flow. GPM equals BTUH divided by the product of delta T times 500. We talked about air separators and air control. We talked about pipe sizing guidelines that you see over here. And then we talked about the whole concept of pumping away from the point of no pressure change. What is the point of no pressure change, and how does it's kind of like the governor. It sets the initial pressure of the system. Pump towards it, then that's the pressure you're going to have throughout the system. And when the circulator creates its pressure differential, it lowers the pressure on the inlet side. You pump away from the point of no pressure differential or no pressure difference. The point of no pressure change. Oh God, we got to work on the mouth tonight. Then we're adding the circulator's pressure differential. So
You need to start drinking.
I don't have a drink here. That might be it. I might need a little help here. So that's where we left off last week. Tonight we're going to start down the journey of circulator selection. And again, a lot of folks look at this and say, well, I just use a 3-speed. Okay, great. What speed do you usually set it at? Well, I usually set it to high, contractor no callback mode. Well, then you don't have a 3-speed pump. You're putting the biggest possible pump you can within that selection, and it may quote unquote work, meaning people aren't freezing to death, but there's a whole boatload of other things going on here. Okay. So those are all things those are things we're going to talk about tonight. We're going to talk about different types of circulators. We're also going to, excuse me, start the discussion. It's going to continue into the next couple of weeks about variable speed circulators. And again, I've heard the story. Yeah. Oh, don't worry about circulators. Just throw a variable speed in there. It'll be fine. These things are magic. These things take the thinking out of it. Well, we're gonna poke a few holes into that hornet's nest as well next week. So let's get started on circulator selection and the whole thing about pump curves, shall we? First things first, we call these things pumps, right? Everybody calls them a pump. We're a pump manufacturer, we're a pump company. These things are pumps. We need a pump. What's the right pump? Blah, blah, blah. Well, we're going to use that word because it's easy, it's convenient, and we're used to it, but it's not a pump, it's a circulator, and there's a difference. Now, a pump is more like a well pump, right? We are lifting water up out of the well into a pressurized tank. A circulator actually does a lot less work. A circulator doesn't pump. A circulator circulates, right? Very good. So it's not a pump, it's a circulator. In fact, maybe a better word for it or better name for it would be to call it a pressure differential machine. Its job is to create a pressure differential within the system, and then Mother Nature takes over. High pressure goes to low pressure. The trick is we need to get a circulator that creates enough of a pressure differential to create enough flow to deliver the BTUs we need under design conditions. And remember that flow is GPM. GPM equals BTUH divided by delta T times 500. It starts to come together a little bit. So we need a circulator that's big enough without being ridiculously oversized. All right, so that's the challenge that we face. And let's start by discussing how the water actually moves. All right, how the water actually moves. And I just got a text from Anthony Tosco, who's got his guys out there down there in Philly, who you're all together. Just a shout out to you guys. I see a picture of you right here, where you're all in the shop watching the show. So excellent, glad you're with us. How does the water move? How does one of these things work? Well, you've got the circulator, all right? You got the gazinta side and the gazouta side, and inside that volute, all right, that casing is this thing. It's an impeller, all right? There's an artist's rendition of what we would call a closed veined impeller right here because there's plastic on both sides. And then over here is a picture of a standard efficiency 007 impeller, which is an open-faced impeller or an open-vaned impeller. They have different jobs. They do different things, but they work in essentially the same way. The water is going to enter the impeller through the eye. So it comes in the gazinta side, and then there's like a hump on the volute. And what happens is that hump redirects the water 90 degrees. So it enters the eye of the impeller. Now this impeller is spinning, all right? It's spinning at a certain RPM, and the water enters the eye of the impeller. Now these vanes that you see in here, these vanes will actually slap and fling the water from the inside out. All right, it's flinging the water from the inside out like that in a 360-degree pattern, adding velocity to that fluid. The discharge side, which is a narrower passageway, turns that velocity into pressure. All right, kind of like if you were to put if you had a hose and you put your thumb over a little part of it, that increases the velocity and the pressure, so to speak, on a hose. Well, this is kind of the same thing, maybe a little different. All right, so that discharge side, that narrowing passageway, turns that velocity into pressure and creates the pressure differential. All right, now a couple things about impellers. We're concerned about the diameter, okay, how big across it is, as well as the thickness, The thicker the impeller, okay, the thicker the impeller, the more room there is for water. So at a given RPM, a thicker impeller will create more flow. It will move more gallons per minute. All right, it'll move more gallons per minute at a given RPM than a thinner one will. In terms of diameter, the larger the diameter, the bigger across it is, the longer the fling at a given RPM, meaning flinging the water from the inside out, the more head pressure differential the circulator can create. Okay, so the thicker the impeller, the more gallons per minute, the larger the diameter, or another way of saying it, the bigger around it is, the more head pressure differential it can create. It could be a higher head pump at a given RPM. And one thing about RPM, if we increase the speed, we get more of both flow and head pressure differential. So a 3-speed pump, simply, if you've got a pump curve here and at low speed and you turn it to medium speed, it goes boom, it just jumps up it stays the exact same shape. It just jumps up a little bit, and you put it into high speed, boom, it jumps up a little bit more. All right, and that's just changing the RPM. It doesn't change the shape, it doesn't change the style of pump or the characteristics of the circulator. It simply gives you more of whatever the heck it was giving you before. Let me know, folks, if that makes sense. All right, let me know if that makes sense to you. And if there are any questions on that, again, as we said, type in your questions throughout the presentation and we'll address them as best we can. But let me know if that's working for you, if that makes sense. And if we're rocking and rolling on the impellers, because this is kind of important when we start looking at different types of circulators and the proper applications. A lot of the different types of circulators can be found right here. Let me give you an example. All right, I'm going to draw for you. Here's a pump performance curve chart, and over here we have head pressure, and down at the bottom we have flow in terms of gallons per minute. A TACO 007, for example, is going to have a pump curve that looks kind of like that. All right, that's a 007, and it's a relatively speaking high flow, relatively speaking lower head flat curve circulator. Now the TACO 008 is going to have a pump performance curve that looks like that. It's a lower flow, by comparison, it's a lower flow, but a higher head circulator. Lower flow, higher head. I have a pop quiz for you, and please type in your answer. Which of these circulators, the 007 or the 008, do you think has the higher horsepower motor? Which one of these has the higher horsepower motor? The high flow, low head circulator or the low flow, high head circulator? That's a good question. I'd like to kind of find out where you're at here. Which one has the higher horsepower motor? We got yeah, we got we got a little bit. You know what? They are in fact the same. They are in fact the same. They're like a 1/25th horsepower motor. They're not, it's not a big motor, 1/25th horsepower motor. The difference in the circulator performance is in the impeller. All right, remember we told you about the shapes of the impeller. The 007 is a high flow pump, so the impeller is going to be fairly thick, relatively speaking, but it's a low head circulator, so it's not going to be that big around. The 008 being a lower flow circulator is going to have a thinner impeller, but since it's high head, it's going to be bigger around. So they're going to be going at the same RPM. At the same RPM, the 008 with that impeller is going to provide less flow, but more head pressure differential. The 007, more flow, but less head pressure differential. All right.
So
Just
they
again,
they look the same on the outside. All
right.
right. The cover plate's going to be different because it's going to show you a different model number. But remember, they're not interchangeable. So you can't take parts out of one and put them into another, because also the casing or the volute that they go into aren't the same either. So there's different tolerances that you have in there. So just so you know that they may look the same, but they are totally two different circulators.
Right. The machining is different, etc. But that's the biggest fundamental difference. The motor's the same, but the cartridge and the machining and the casing completely different, to create the different types of performance. Now we're going to get into when you might use a 007, when you might use a 008, and really a 008 is kind of, the pump curve on a 008 is kind of like the high speed curve on your typical 3-speed pump, whether it's a Taco 0015 standard efficiency, the Grundfos 1558, B&G NRF 22, pick your favorite flavor. They're all very much the same basic pump performance curves, but they all are that lower flow, higher head, steeper curve pump that are it's a very good pump for specific applications. All righty, very good, very good. Let's talk about head for a minute. Now, head in our world is a term for expressing pressure, or in the case of circulators, head pressure differential, all right? So head in this case is a term for expressing pressure. We talked about this last week, that a column of water 2.31 feet high will have a gauge pressure down at the bottom of 1 psi, So that's, so 2.31 feet of head loss is like saying we have 1 psi worth of pressure loss. Okay, it's the same thing, only different, just expressed in different terms. Now, the pressure loss that we're going to experience in the system comes from the piping and all of the components, all right? Water's rubbing up against the side of the pipe, it's ramming into fittings, it's going through zone valves and things like that. All of those things create pressure loss or friction loss, and the circulator has to overcome that pressure loss, all right? So that's where what the word we use for head. And again, 2.31 feet of head loss is equal to 1 psi of pressure loss if you're looking at pressure gauges, all right? Now, other ways of looking at head, we have 3 different kinds of head that we're talking about in hydronics. The first is static head, or static fill pressure is another way of looking at it. That's the pressure you need to fill the system to its highest point, with keep it filled, pressurized with a little bit left over. That's typically the 12 psi that we discussed last week. All right. There's friction head, or friction pressure loss. That's what's going on in the piping system. As the water goes through the piping system, that piping system is going to impart friction loss on that fluid, and it's going to result in pressure loss. That's what we have to overcome. All right, we have to figure that out, and we have to overcome that with the circulator. And then there's pump head or circulator head. That's the pressure differential the circulator is capable of producing, and we will show you that in our pump performance curve charts. All right, that outlines what the circulator can in fact do. Now we want to make sure that what the circulator can do meets or just slightly exceeds what kind of friction head we're encountering in the system. All right, Let me know if that makes sense to you, because there's a lot of moving parts here. But these are the 3 types of head that we typically deal with. Now, here's an important truth, and again, I think most of us are pretty clear on this, but this question does generally come up more often than you'd think. The physical height of the heating system above the boiler has nothing, nada, nothing to do with the required head pressure of the pump in feet of head. Feet of head is an unfortunate term, and that we often look at feet of head and we think feet of height. All right, well, I gotta pump that water all the way up to the 4th floor here. I need a high head pump. I got to pump it all the way up there, man. Well, no, you don't. Okay, they have nothing to do with one another. Getting the system filled and pressurized up to its highest point, that's your static head. That's the fill pressure when you initially fill the system. All right, when we fill the system, the entire piping circuit is filled and pressurized with water. So when the circulator comes on, that circulator doesn't have to lift the water up to the 3rd or 4th floor. It's already there. All right, it's already there. So I don't have to lift it up. It's not an open system, it's a closed system. In addition, the guys say, well, what about I got to lift the weight of the water, don't I? No, you don't, because it's a closed loop, right? It's a closed loop. And I don't have to lift the weight of the water because the same amount of water is coming back down the other side on the return side. So that's why circulators do so much less work than like well pumps. All it has to do is circulate. All it has to do is circulate within a closed loop system. So very important, the physical height of the heating system above the boiler's got nothing to do with head pressure of the pump in feet.
Can I
Think
add
of it.
something?
Sure, go right ahead.
The same thing applies for potable water systems, and people will forget that because in their mind they think a potable water system is an open system. Oh, therefore I got to go to the 3-story house. No, you don't, John. And it's because it's still a closed system, and they start oversizing those pumps. Anyway, we see it. We're mostly talking about closed loop heating and cooling stuff, but it applies to applies to domestic water systems as well. So when you're doing domestic hot water recirculation, don't start adding the height of the building just because it's potable water. Go ahead, John. I'm sorry.
You're right. You're absolutely right. It's exactly the same process. It's friction loss through the piping. We don't have to lift or anything like that. Very good point. Maybe the best way in both instances to think of this is to think of the circulator as you would think of the motor on a Ferris wheel. All right, the Ferris wheel. If Rick, Dave, and I are in that little cart right there, all right, the motor doesn't have to lift our heft up, right? Because there's 3 other, dumb fat guys on the other side going right back down, right, just opposite of us. So we don't have to lift. There's the same amount of tonnage coming back down the other side. All the motor on the Ferris wheel really has to do is overcome the friction loss of the bearing assembly right there. All right, again, think about it. You ever see them load a Ferris wheel? They'll put you on, this guy gets loaded up down here, and then he goes way up at the top, and then the cart directly opposite them gets filled. That's because of the power of the motor. So they don't just load cart after cart after cart after cart. That would be crazy. It doesn't work that way. So think of the motor, think of your circulator like you would think of the motor on a Ferris wheel, and the water is just like all the different carts. Maybe a better visual is this. Think of the circulator as your bicycle pedal, and think of all of the water in the system as the bicycle chain. All right. When you pedal the bicycle, every link in that chain moves at exactly the same time, at exactly the same speed. So I start pedaling here, this chain starts moving just like this chain. All right. Same thing within a hydronic system. The minute the circulator comes on, this water starts moving, but so does this water and all of this water and all this water, and it moves at exactly the same speed. All right.
Yeah.
So just a good visual. All righty. How are we doing? Any questions out there, boys and girls? How are we doing out there?
None at this point.
All right. Very good. No snow in Nova Scotia yet, right? Make sure you pedal at 85 to 1,000 RPM. Yes, Jim, yes. We got to pedal in a hurry. All right. When we look at Taco's fixed speed circulators, we got a boatload of them. And if you were to put them all on one pump curve chart, it would look ridiculous because there's so much stuff and it would be virtually unusable. So we like to break them up into families. First, we have the we have the 003 and the 006. They're little circulators, low flow, low head, not a lot of oomph to them. These primarily are your domestic hot water recirculation pumps because those don't require a whole lot of pump really in most residential applications. It doesn't require much flow and there's not a whole lot of head loss to overcome. So those are the little ones, the 006, 003, 003, 003B. 003B is bronze, 006 it can be had in stainless steel or cast iron for heating applications. We see them a lot of times. These were used for variable speed injection mixing back when we did a lot more of that than we do today. And small pump does a lot of work in an injection mixing situation. Then we have our flat curve circulators. Again, flat relatively speaking, okay, they're high flow and relatively low head, the 005 and 007. The 007, of course, is the workhorse. 0010 is kind of a B&G 100 replacement in many cases. And then for even bigger applications, we have the 0012. All right, high flow, low head, flat curve they work outstanding in most zone pumping applications, and they're particularly flat curve pumps are zone valve pumps. If you're using a steep curve pump in a zone valve application, you should probably rethink that, and we'll explain that in the coming weeks. But a flat curve pumps and zone valves go together like cake and ice cream. Steep curve pumps and zone valves go together like tuna fish and ice cream. In other words, not very well. But we'll get into all of that in upcoming sessions. Our steep curve pumps, of course, we have the 008, as we mentioned earlier, and then its big brothers, the 0011 and the 0013. Again, radiant floor heating kind of lives right in here. That's a great application for a steep curve pump. These guys, snow melting, heat exchangers. A lot of times they're used on boiler pumps for larger ModCon boilers. You'll see them as pumps for indirects as well in many cases where you have where you need a lot of recovery, and there's a high head loss heat exchanger there. So that's where you'll see the larger steep curve pumps. We have the red-headed stepchildren, the specialty circulators that don't really fit anywhere. Okay, the 0014 used a lot. It's a very common pump, but it's not really steep. It's not really flat. It's kind of fleep, if you will. But then we have the double black diamond, if you're a skier, the 009, which was originally conceived as a booster pump for drain-back solar systems. Drain-back solar systems is actually an open system, so there the height matters. All right, so there's a high head pump right there. All righty, and then we got a lot of 3-speed. I think we have as many 3-speed pumps, if not more 3-speed pumps than anybody else out there in the business. We have the 0015, the smaller of our standard 3-speed pumps. Again, you'll find these pump curves to be very, very similar to other common 3-speed pumps out there. You know, the 1558, the NRF 22, and any of the others that you'll see out there. Again, they're virtually interchangeable. And then the 0013, again, it's just a higher head, higher flow version of the 0015 as a 3-speed circulator. We also have 2 flat curve pumps, and they don't really look flat here, but that's just because of scale. We have the 0010 flat curve pump, which is really a great service pump for those B&G 100 types of applications. And then the 0012 3-speed, again, 3 speeds for higher flow rates and higher head losses for larger type of systems. So we keep you covered there. ECM, we got a boatload of ECM circulators. I'll just cover 2 here real quickly. The 007 ECM variable speed circulator. It's the 007E, kind of the ultimate flat curve circulator, really good for zone valve applications. And if you like to use 3-speed standard efficiency circulators, you'll love 3-speed. You'll love the 0015E3, which is a 3-setting variable speed ECM circulator. This actually is a great zone valve pump as well. So that's kind of the family of circulators that we're talking about here, the different families of circulators. So again, imagine if we tried to put that all in one chart, you'd lose your mind. Okay, so it's as wide of a range of circulators as you'll find in the hydronics industry. All righty, You guys ready for Takeo trivia question of the night? We've been cruising along. Are you boys ready? Dave, Rick?
Let's go.
All right. Now, whenever you bring up Schoolhouse Rock, any kid who watched that was the first thing John Messenbring said earlier was he started singing Conjunction Junction. So this trivia question has to do with Conjunction Junction, that classic 3.5-minute Schoolhouse Rock episode. It came out in 1975, and it's really, I think, Schoolhouse Rock's most famous segment, 1975's Conjunction Junction. And the lyric that everybody knows and everybody sings is Conjunction Junction. What's your function? See, there we go.
A couple of guys typing it in already too. Yep.
All right. But that's not the trivia question. The trivia question is kind of a two-parter. As per Schoolhouse Rock, what is the function of a conjunction? And what are the 3 most useful conjunctions? Yes, this is hydronics meets grammar, my friends. All right. Good grammar is very important. Without good grammar, we don't got nothing, right? So what is the function of a conjunction, and what are the 3 most useful conjunctions according to Schoolhouse Rock? All right. We will have the answer for you later, and then we will have valuable prizes, including all kinds of really cool stuff that Dave has in his garage. All right.
And a new
Dave's
car.
garage.
And a new car. There you go. Okay, so I can hear everybody saying, "That's forget the rest of the webinar. Let's find the answer. Get on YouTube. Get on Google. Let's figure this out, man." All right, but knowledge is power, friends. Knowledge is power. So we're going to get right back to work because knowledge is power. So let's size a circulator, shall we?
There's some questions there, Johnny.
There is. Let's see. What do you got?
Yeah, there's Justin. How about a blend pump for boiler and or sizing them? I think maybe blend means mixing, like injection, variable speed injection mixing. There's we just use the universal hydronic formula, Justin, and we just look at the delta across the 2 injection legs, and that's how we figure out how many GPM we need for injection. And then the one from Mark Fahey. See that one, John?
Yeah, what sizing formula do you prefer when when sizing circulator pumps for air to water, heat pump in-floor systems with buffer tanks, backup boilers, etc., compared to oil or gas-fired systems? That's a great question, Mark, and it's the same. There's one formula for sizing a circulator, but it's because we're talking about friction loss, whether it's going through an air, for whether it's going through the exchangers in an air to water heat pump, or an indirect water heater, or a ModCon boiler. It's the same. If I'm understanding your question correctly, it's going to be the same formula, which we're going to do right now.
You still need to know the flow and head. Exactly right. Yep. So it's going to be the same thing no matter what. You got to move water. You got to change the delta T's based upon the application, whatnot. So it's all going to be the same. So let's take a look at it.
All righty. So here's the formula. Here's the process. Let's look at it this way. Here's the process for sizing a circulator. All right. We're going to do 1 zone of fin tube baseboard. Okay. And it really doesn't matter. It can be pretty much anything, but we're going to do 1 zone of fin tube baseboard. And this zone of fin tube baseboard has 30,000 BTUs on it. It's a big honking zone. All right. We did the heat loss. We didn't measure the baseboard and say 30,000. We actually did the heat loss of the rooms in this zone, and that heat loss came up to 30,000 BTUs. Okay. We're designing the system to a delta T of 20, meaning the water goes out at 180, comes back at 160 for an average of 170. And in this example, we're going to use 100% water. So remember, GPM equals BTUH divided by delta T times 500. So we put in what we know, 30,000 divided by 20 times 500, all right? 30,000 BTUs divided by our delta T of 20 times 500, 20 times 500 is 10,000. To find the required flow rate for design conditions, 30,000 divided by 10,000, that gives us a required flow rate of 3 gallons per minute. So my circulator, let's say it's this circulator right here, that circulator is going to have to give me 3 gallons per minute of flow under design conditions. Now, 3 gallons a minute ain't a lot, all right? It ain't a lot. But we know that's what we need. Now we have to figure out the head loss. What is the head loss of that piping circuit so we can finish the job of selecting the circulator? And again, if it was any of these other things that you had mentioned earlier, heat pump or whatever, we need to know the pressure loss through all of the different components, all right, at the specific flow rate, because that does matter. But let's just look at this as a basic piping circuit, if you will. The first thing we're going to do is we're going to do the estimating way. This is your 4 o'clock Friday afternoon. I got to put a pump in here. What do I do? So this is a way to estimate head loss. This formula that we're going to show you is wicked easy and it's wicked safe, meaning it is safe. There's a lot of fudge built into this that you'll never be undersized here, provided the pipe size properly for the flow. But let's estimate our head loss. So the first step is to measure the run as best you can. All right, now you don't, if it's a, you're replacing a pump, they're not going to give you free rein with a sawzall to hack up the house just to count the pipe, right? In this case, you're going to have to estimate the length as best you can. But we need to know the run, and the run is going to be from the Gazouta side of the circulator all the way back through the system to the Gazinda side of the circulator. That's the run we're talking about.
So and don't spend a lot of time doing it. This is not going to be if it's a baseboard, it's perimeter heat. You're done. What's the length width of the house times 2 for each side? Call it a day, done. It should never be 83.5 feet.
Right, exactly. You might look at the boiler and say, okay, first we're going up 5 feet and over 5 feet. That's 10 feet. Then we're going to go down 40 feet. Okay, that's 50 feet. Over 20, that's 70 feet. Back 50 feet, that's 120, right? Over 10, that's 130. Down 10, that's 140. Call it good. All right, we'll call it good. That's really the least you should do. So measure the run.
Not the height, Bill. Not the height, Bill. Okay, we only have to worry about the length of pipe it took to get there. We don't have to worry about the height to get there. Okay.
Yeah, remember, circulators don't care about the height of the heating system above it. Doesn't matter. Doesn't matter. We don't have to factor in how tall the building is, other than measuring, other than knowing how long that of a run of pipe that is. All right, we don't have to factor in height as another variable. All right,
I'm guessing he was joking.
Oh, gotcha.
I think he was yanking our chain.
I know, but it was actually perfect for me to add it back in just as that reinforcement too. So thank you, Bill. Now I know.
All right, Bill. All right, so we measure the run, and then we have to factor in fittings and stuff, right? Because we can't count those. And fittings have pressure loss that's equivalent to lengths of pipe. So we multiply that by 1.5. We measure the run, and then we multiply it by 1.5. We add 50% to account for fittings and stuff that's in the way. That gives us our total developed or total equivalent length. Now, to estimate the head loss, we'll then multiply that number by 0.04. 0.04. That represents 4 feet of head for every 100 feet of straight, properly sized pipe at the maximum flow rate for that size of pipe. Remember back to last week when we sized pipe, right? So 0.04, 4 feet of head for every 100 feet of straight, properly sized pipe at the maximum flow rate for that size of pipe. So we're estimating the highest possible head that could be in that system at the highest flow rate. That's what we're estimating. So let's do one. Measure the run, multiply by 1.5, multiply by 0.04. So let's do this. Here's our zone, and we measure the total run to be about 135 feet. Okay, 135 feet. First step, multiply by 1.5. That gives us 203 feet. That's our total developed or total equivalent length. That we're going to multiply by 0.04. And that's going to give us just about 8 feet ahead. All right, 8 feet of head. So when I go to look for a circulator, I'm going to need a circulator that's going to give me 3 gallons per minute worth of flow while overcoming 8 feet of head. 3 gallons per minute while overcoming 8 feet of head. All right, very, very good. So what does that mean for a circulator? Well, let's pick one. And here's one of those charts I was telling you about where we got every circulator we make on one chart, which is just nuts, but here it is. But we're using this for a purpose. Again, down below, we have gallons per minute. And then over here, we have head, right? So 3 gallons a minute, 8 feet ahead. Here's my requirement, right where that red dot is. Now, taking a look at the red dot, what circulator would you choose? Type in, let's see what you have for thoughts. What circulator would you select of the ones shown here? All right, what do you got? What do you got, people? And Carl, you're right. Wouldn't it be easier to multiply by 0.06 and save a step? Yep, you certainly can. However, it's good to know how you arrived at 0.06. All right, very good. 005, if you can find one. You know where we're going with this, right? Yeah. Okay, very good. Most people are saying 005 and 007, and I think in either case, you're going to be fine. In either case, you're going to be fine. The thing is, the 005 is in every sense the 007's kid brother, all right? It's the 007's kid brother, but it's also living proof that you guys don't buy on price. Another story for another day, but that's the point behind the 005. Most people don't stock it. You find it at Grainger, catalog stores, things like that. They actually do buy a lot of 005s. But most folks will find the 007 is going to be the right combination of price and availability. Okay, the 005 is going to actually wind up being more expensive simply because we don't make as many of them. But the next question I have for you is, first we have to understand something. If I chose the 008, this one, if I chose the 008, would it work? All right, would it work? And B, what kind of flow and head would the 008 deliver? All right, understand this about system. When you put a circulator on a system, that circulator takes over, right? That circulator's in charge, man. When it's on, bam, it's on. It's working on that pump curve. So no matter what, it doesn't matter what the system needs. The system's going to get what the circulator tells it it's going to get, all right? And the circulator has to work somewhere on its pump curve. Energy in equals energy out. So if I put the 008 on here, that system's going to have to work somewhere on that line. My question to you is, in terms of flow and head, where do you think it's going to run? What flow are you going to get? What head are you going to get? All right, when you put the 008 on there, all right? Let's see what we got. Let's see what we have. We got a couple of answers here. 008 will provide higher flow and head towards the top of the curve. Yeah, we have extra flow, right, Randall? Very good. Yep. You guys are right. 6 at 13 per Carl. There you go. Flow and head will be higher. Yes, we're going to work on the pump curve. Now, I've had people say, well, if you put the 008 on it, it has to work right at, it has to work out here because 8 feet is the head. So you're going to have, it'll give you 10 gallons a minute. No, the head's not the limiting factor here. The head is not the limiting factor. We have to understand a concept called the system curve. The pump curve we figure out, all right? A system curve, and in subsequent sessions, we're going to show you how a system curve is arrived at. But a system curve is a theoretical curve that tells you the head at different flow rates. As the flow goes up in a piping circuit, the head loss will go up exponentially. All right, it just shoots up like a rocket ship. We know 2 points on the system curve. We know 3 at 8, but we also know 0 at 0, right? Mathematically, we could figure out, okay, what's the head at 1 gallon a minute in this piping circuit? What's the head at 2? I know what it is at 3. What is it at 4? What is it at 5? What is it at 6? And we can math that out, but it's going to look something kind of like this. All right, it's going to look kind of like this. Oh, let's say it's going to look kind of like that, depending upon the system. It's going to shoot up like a rocket ship, not necessarily in a straight line. So at 3 gallons a minute, I need 8 feet ahead, right? But if I chose the 008, I'm going to be up here at what looks to be at about 4 gallons a minute at 14 feet ahead. All right, 4 gallons a minute at 14 feet ahead. Is this thing going to work? Oh, hell yes. Can I deliver 30,000 BTUs with 4 gallons a minute? Sure as shooting. But please remember this, GPM equals BTUH divided by delta T times 500, right? That's not just a good idea, it's the law. Now, 30,000 BTUs is the load I need under design conditions. It doesn't matter if I could get more, I don't need more. I need 30,000 BTUs, that's the load, all right? Now, my delta T is 20 times 500. That should give me 3, right? But I'm not delivering 30,000 BTUs with 3 gallons a minute. I'm delivering 30,000 BTUs with 4 gallons a minute. If I'm delivering 30,000 BTUs with 4 gallons a minute, what has to give here, people? Something's got to give so this math works. What is it? What's got to change? Give us your idea. What has to change? Do. What do you think? What do you think? What do you think? Yeah, man, not the BTUH, not the BTUH, the delta T. The BTUH is the load. That's not changing. Doesn't matter if we could give it more. It doesn't want more, nor does it need more. That's the load under design conditions. What has to give is the delta T. It's not going to be 20. I'm giving, well, it's only 1 gallon a minute more. Yeah, it is, but it's also 33% more flow than I need. I need 3, I'm giving it 4. That's 33% more flow. That will translate into a 25% lower delta T. So that delta T is not going to be 20, it's going to be 15. So it means the water's going out at 180, coming back at 165. Yeah, I'm going to have a slightly higher average water temperature, but that's not the point. The point is the water's not coming back at 160, it's coming back at 165 on the coldest day of the year. What is that going to do to the boiler? What is that going to do to the boiler? And if anybody types in anything other than short cycling, we're going to start the class over again. It's going to make that boiler short cycle on the day of the year where it wants to short cycle the leastest. I've had guys say to me, and these are well-respected, quote unquote experts in our industry, says 20-degree delta T, yeah, that's meaningless because I've walked into mechanical rooms and I've never seen a 20-degree delta T. Well, if you understood how systems really work, you'd know why. Okay, you very rarely, if ever, see a 20-degree delta T because we overpump, man. And even if we didn't overpump, the only time you'd see a 20-degree delta T is on the coldest day of the year. All right,
Because everything was perfectly sized.
30,000 BTUs. Yeah. Go ahead, Dave.
And if everything is perfectly sized.
Right.
Perfect alignment to the planets. All the zones are calling for heat. They're all set for 70 degrees. All that jazz in between, as you've said before, cats, dogs play well with each other. It's Christmas, New Year's, your birthday, all rolled into one. Yes.
Right. Yeah. The moon is in the 7th house. Jupiter's aligned with Mars. Love guides the planets and all that stuff. Yeah, that's when we would get that. That doesn't mean it's not a good thing to shoot for. All right. That doesn't mean this is okay. It quote unquote works. No one's going to freeze to death, but this is going to get worse. Okay. Because I'm always giving this 4. Every time that pump comes on, I'm always giving it 4. What if it's 50% load? All right. What if it's 50% load, not 100% load, meaning it's warmer out. It's a warmer day in the wintertime. And the load is really 15,000 BTUs. Okay, instead of being 0 degrees outside, let's say it's 35 degrees outside. The load's only 15,000. Remember, the BTU load changes with the weather, right? But I'm still ramming and jamming here at 4 gallons a minute. This isn't going to be 15. This is going to be 7.5. Talk about now we're making that boiler short cycle even more. And understand this, boys and girls. Statistically speaking, you will spend 50% of your heating season at 1/3 load or less, not at 1/3 load, bam, at 1/3 load or less, 50% of your normal heating season. That's 10,000 BTUs. What that means is we're going to be spending most of the heating season with a delta T of less than 5. Tell me that's a good idea, all right? No one's ever going to freeze to death. No one's going to freeze it, but what does that do to the efficiency of the boiler? What does that do to the lifespan of all of the moving parts in the system? What does that do to the wear and tear on all of those life parts? This is not, and this isn't crazy oversized either, boys and girls. This is not a crazy oversized pump. If we had chosen the 007, we'd be better. We wouldn't be perfect, but we'd be better. All right. We would be a little bit better. We're still going to have the same problem though. All right, just not as severe. So this is what I meant earlier when I said that circulator has more to do about overall system efficiency than we've ever given it credit for before. All right. And you want to know what else? This is an unrealistically rosy scenario because we estimated head loss. This isn't real. This is unnecessarily rosy. Let's take a look at this, how we can even make this worse. What if we were to go with a 3-speed circulator? All right, this is where I need to be. Personally, I'd be fine with low speed here. If this was me, I would use a 0015 and I'd put it at low speed right here. But where do people set 3-speed pumps? We all know where people set 3-speed pumps. It's contractor no callback mode. It's not medium. Medium speed, nobody uses medium speed. That's for people with commitment issues. You go high, man, you go all the way. If we went all the way here, put it on high speed, now I'm jamming at 5 gallons a minute and my delta T situation is just that much worse. Again, no one will ever freeze to death. This is where people look at me and say, that's insane. I put those things in and it works. Well, let's define works. Nobody's freezing to death and blaming me. That's your first hurdle. All right. That's not the end of the job. You know, a handyman can do that. You're a professional. They're expecting a little bit more from you.
And sometimes they end up in low speed. They start off in low speed, right?
Mhm.
You start off in low speed, you install it, you turn it on, it runs. You're like, okay, this is all pretty cool. You clean up all your tools. You're starting to walk out and you look at the circ and you're like, no, I'm going to turn it on. And you turn it up before you walk out of the house.
Yeah, nobody wants that phone call, man. Nobody wants that phone call.
Exactly. And you don't want to take that walk back. It's like the walk of shame, you know. Okay, I go downstairs, and you walk downstairs and you go click, click. And is that the only thing you do? Heck no. Right? You all of a sudden you start banging on pipes, making some noise. You check your Facebook feed, register for takeaway after dark and stuff like that. And then you walk upstairs and okay, I got it going. It's all good now.
Now I want to show you how unrealistic that was, or how hopelessly optimistic that was, because we estimated head at the highest possible flow rate for 3/4 inch pipe for that zone, but we weren't at 4 gallons a minute. That wasn't the required flow rate. The required flow rate's really 3 gallons a minute. So if we actually calculate head loss rather than estimate it, you're going to see it's something kind of interesting. So this chart comes from the Copper Development Association's Copper Tube Handbook, maybe the most mind-numbingly boring book ever written, except for Table 6, which is a pressure loss chart of water due to friction in types K, L, and M copper tubing, and it gives you the pressure loss in PSI per foot of tube. Keep that in mind. It's PSI per foot of tube. So let's take a look. All right. We're looking at 3/4 inch type M copper. That's what we would use for 3 gallons per minute that's the required pipe size for that required flow rate. So I find my 3 gallons a minute, I find 3/4 inch M, and I see that my pressure loss in PSI for 1 foot of pipe is 0.009. So it's 0.009 PSI worth of pressure loss per foot of pipe. Now I just got to figure out how long my run is. All right. Now I can use the 203 number I had earlier. That's a perfectly acceptable number in this example. If you really suffered through excessively rigid early toilet training and everything had to be just so, well, then you can use this chart. All right. This gives you the different types of fittings, and it's the equivalent length of pipe. So what this is telling us, I got a 1/2 inch 45, 1/2 inch copper 45 is worth 1 foot of pipe from 1/2 inch all the way up to 1.25 inches. So 1 1/4 inch 45 is also worth a foot. Those are all worth 1 foot of pipe. A 90 is worth 2.5 feet of pipe all the way up through 1.25 inches, then 4.3 at 1.5 inches, 5.5 at 2. Full port ball valves you see here, globe valves are kind of a balancing valve. That's what that is. Here's the T's, a Venturi T, and flow checks, weighted flow checks. Those are the equivalent lengths of pipe. All right.
And
so
if you look at those for a second, pay attention to what the globe valve shows you, the Venturi, the flow check. Those have really high pressure drops. You know why?
They're
supposed to.
Right.
They're supposed to. A globe valve is a balancing valve, right? It's used to balance. It's used to use that pressure drop. When you take a look at ball valve, you don't balance with a ball valve. Venturi T is created to create a pressure drop to force the water to flow in the other direction. So just pay attention to that. So sorry.
No, very good, very good. So as an example, you'd count them up and see what the total equivalent length is of all of your fittings. In this case, 65 feet, to add it to the 135 and we had for measured length, we come up with 200. Like I said, you could have used the 203 that we came up with earlier. So 200 feet of pipe times 0.009 psi per foot of pipe gives us a pressure loss of 1.8 psi through that piping system. Now we already know how to convert psi into feet of head, right? We multiply it by 2.31. So 1 psi times 2.31 feet of head per psi, this is the real head loss, just over 4 feet of head. We estimated it at 8. It really is only 4. All right. So if you add, so look at it like this: if the flow goes up 33% from 3 gallons a minute to 4 gallons a minute, the head's going to double. That's the mathematical relationship between flow and head. So what I really need is 3 gallons a minute at 4 feet ahead. Looky-loo, that's down there. That's why I said low is just fine. Low is going to be more than enough here. If I were to calculate out my system curve, and here are the different operating points. Now in this case, again, I'm at almost 4 feet ahead at low. All right. I'm at almost 4 feet ahead at low speed. So I'm still over pumping. But if I went to high, if I said 135 feet, that's a long, so it's 30,000 BT freaking U's, man. I better make sure I get flow. Click, click, let's put it on high and get the hell out of here. Look at this. I'm at almost 6 gallons a minute. It's amazing. If I had ever saw delta T in double digits, I probably won't. All right. This is the problem, people. We have a chronic overpumping problem in residential hydronics because of this.
Chronic indeed.
Yeah, and just imagine the issues that tends to lead to. First off, you've got systems that are never as efficient as they could or should be, especially the new high efficiency systems that people are expecting big numbers out of. Yeah, the combustion efficiency looks good, but they're not as fuel efficient as they could or should be, and not as efficient as customers are expecting, as we have learned over the years. But we're short cycling things into an early grave. If you've had to replace an igniter, an ignition module, a blower motor, any kind of a spark ignition thing, any kind of a moving part in that boiler prematurely, it's not because they're using crappy components these days. All right, it's because we've probably short cycled them into an early grave. That's what we're dealing with.
And we've been doing it this way for decades.
Yeah.
Almost a half a century. Right.
So
but actually, for the last 25 years, the circulators have changed to sometimes some more steeper curves than the flatter curve pumps. We didn't see it as much with, say, the B&G 100, the Takeo 110s, but as we get steeper, that's where we start seeing more of these issues come into play in the last 25 years or so. Does it work? Yeah. For how long? Exactly.
Yeah. And really what we're seeing is the thing that's really exacerbated this has been the advent of steep curve 3-speed pumps, which, again, designed really for European type of applications, not so much for the types of applications we put in here, outside of radiant floor heating, but they were shoehorned into systems that we did here because people love the button. They love the dial. Man, I got 3 speeds. This is the only pump I'll ever need. It was a nice story, largely bullshit, but it was a nice story. So we started shoehorning these things in. So then we started seeing all these problems. What made the light bulbs come off was the advent of variable speed pumps, because then we realized it doesn't have to be this way. It doesn't have to be this way. So that's kind of the story about system curves and pump curves. But I want to show you just another curveball, man. What if we had the same length? We were still at 200 feet, all right? But it was a different zone. It was a different zone, and it was only 20,000 BTUs. Different zone, but it was the same length. If we had used our original, measure the run, multiply by 1.5, multiply by 0.04, we would come up with 8 feet, because all that sees is length, right? All that sees is length. But this is load now. 20,000 BTUs is only 2 gallons a minute. All right. So now dig this. Our pressure loss is 0.004 psi per foot of pipe. Again, it's less than half of what it was at 3. All right, it's less than half than what it was at 3. So it's 0.004 psi per foot. This is very interesting. Let's do a little math here. Yeah, 0.8 psi, 200 feet times 0.004 psi per foot. That's 0.8 of a psi. We're talking about 1.85 feet ahead. This is a 135-foot loop with fittings carrying 30,000 BTUs or 20,000 BTUs in this example. 20,000 BTUs. It's less than 2 feet ahead. Realistically, we're looking for 2 gallons a minute at 2 feet ahead. You know what? We're never going to undersize that pump because nobody makes a pump that would be undersized. I got to be down here, man. I got to be down here. Nobody makes a pump that would not be oversized in terms of standard efficiency. An enterprising pump company with your best interests at heart has one that you can use. All right. Just letting you know that up front. We'll talk about it in a couple weeks, but really, this is the best you can do. I'm going to have, in this case, 50% more flow than I need. So my best delta T is going to be about 12, 13 degrees in this system, and that's really not bad based on what you have. But we can do better. We absolutely can do better. And good Lord, look what happens if we were way the heck up here. All right. You know, that I need 2, I'm giving it almost 5. All right. That's 2.5 times the flow. We're not getting out of single digits, people. It's just not going to happen for delta T. Delta T is important. It's not just a design feature and a nice theoretical number. Delta T is important because it's an indicator of the health and the performance of the system. All right. The colder it gets, the delta T is going to get wider. The warmer it gets, the delta T is going to get lower because we're pumping at a fixed speed, right? But we want to keep that delta T as wide as possible for as much of the heating season as possible. That is your pump sizing goal. And the way to achieve that is once you know your flow and head, pick a circulator whose performance curve is as close to, either equal to or as equal to is perfect, but as close to that as possible. All right. A little low might be okay. You know, a little bit higher would be all right too. What you really want to do is you want to eliminate as much white space on the pump curve chart as possible between your requirement and the curve that you're using. That's your goal when we're talking about circulator sizing. All right.
Well put.
Let me know if that makes sense to y'all, because that's kind of good stuff, man. And it's time for our trivia answer. It's time for our trivia answer. Conjunction junction. What's your function? All right. Question, just before we answer this question, don't variable speed pumps help with the problem? Asked Shane Brown. To a degree. They don't magically cure it. It's to a degree. You have to know what you're doing with variable speed pumps. And Shane, this is something that Taco's been very adamant about. These things aren't magic. All right. These things are not magic. These things are they're fantastic pieces of equipment. They do incredible things, but you got to know how to make the most out of them, because you could put a variable speed pump on that job and not help it at all, other than using less electricity if you're not careful about what you're doing. So it's always, you certainly can help it. Again, the advent of variable speed circulators really opened up this whole world to us to be able to talk about it, because we can do better. Before, that was all we had, so but we can do better. So Howard Leggett mentions the VT2218 all day long. Yeah, and twice on Sunday. I agree with you, Howard. Best pump out there.
And that goes back to our
pump.
That goes back to our conversation from last week that we were talking about boiler sizing. Right? We had modulating condensing boilers. Well, just put a modulating boiler in. Not necessarily. It could be too big on its lowest firing rate. So same thing can happen with circulators too. We may not modulate to where it does anything whatsoever to the system except use less electricity. Except your modulating boiler may not be using less fuel. It's still sending out the same BTUs, and the house is still consuming the same amount of BTUs. You're just not seeing that percentage jump that they should have seen going from, say, a cast iron to a condensing, if it ain't condensing. So
can't go any lower than low.
That's right. That's right. That's right. All right, time for our trivia. Try that again. Your first day with the new mouth. Trivia answer. Again, what is the function of a conjunction according to Schoolhouse Rock? What is the function of a conjunction? So, pretty simple. According to these are the lyrics: hooking up words and phrases and clauses. All right, hooking up words and phrases and clauses. All right, that is the function of a conjunction. And what are the three most common conjunctions?
Junctions.
And, but, and or will get you pretty far. Those are the lyrics. And, but, and or. So this and that. Okay, this or that. Not this, but that. All right. Grammar, baby. Knowledge is power. Knowledge is power. All right. Conjunction, junction. What's your function? So we've got what we'll do is we'll collect all of the right answers or reasonably close to the right answers, because this was a weird question. I'll give you that. We pulled this one out of the sky just because I watched that YouTube video about 3 or 4 times earlier this week, and I said, yeah, that's our question. All right, because the song is just so damn catchy. So we're going to get as many of the close to right answers as we can, and that'll be part of our package. We'll select a winner next week. We'll do a little wheel thing that we're going to do right now for last week, and
That's right.
we will be able to. We'll give you a massive prize package of stuff that Dave has in his garage. So some of his old tools, his old high school, football uniform. I think he's still got that out there. What else you got in your garage, Dave?
Number 33 from Polk High. Yep.
Number 33 from Polk High. There we go. All right.
Actually, this for last week, I have a Takeo backpack that I'm going to be giving away this week. Yes, I did find a backpack out there. So, nice backpack. It's got about 4 pockets in there, so you can, throw the tablet or laptop, whatever you need for your job sites, and enough file space in there, and then a bunch of other little pockets all over the place. So.
Very good. All right. Well, I'll do this. I'm going to stop sharing my screen. You've got the wheel all set for.
I do.
This week. All right. I am stopping my screen and I'm going to make you the presenter. Tony Stank. I don't want to know, man.
If you follow the MCU, the Marvel Cinematic Universe, it was in the end of one of the movies. So as Tony Stark.
Okay. That works for me.
Yes. All right, let me make sure. Okay, there we go. This is last week's question. What was last week? I forget already.
Oh, it was about WKRP in Cincinnati.
Ah, that's right.
So I can look up the question. Hold on a second.
Yeah. Okay. Before we hit spin. Okay. So I got everybody's name out here.
You go ahead.
You're gonna look up at the same time.
A couple seconds here. Go right ahead.
All right. So let's get the spinning going on here from everybody that got a right answer last week. Let me pull up my list. And, and it's Mike. Oh, sorry, Mike. I spelled your name wrong.
Mike.
Yeah. Way to go, Mike.
Excellent. Mike, I know you're online tonight with us, so I believe you are. Anyways, but if you can send in your name and address. Your address. I got your name already, so.
For those of us who fly a lot, to me that says Milwaukee Lampkin.
Yeah. Actually, no, Mike is not on with us tonight, so I will have to contact him outside of here in order to send him his stuff. So excellent. So
and the question last week was from WKRP in Cincinnati. What word did Dr. Johnny Fever say on the air to get fired from his original job in Los Angeles? And that word was booger.
Booger. Yes.
Booger. That'll get you fired.
All right, you got the con, sir.
All righty. Well, hey, we're kind of done here in terms of our presentation. What do you got there, Rick?
I don't know. I want somebody that out there in the world that knows what that is. And don't get weird on me. Okay. Tell me if you know what that is and what it's for, just drop me a little message.
Were you using that earlier today?
Anthony nailed it.
Anthony nailed it. Carl Carboni nailed it.
Yeah.
There you go. Yeah, it's a Moen PosiTemp cartridge puller.
There it is, baby.
You guys are good, man.
That job really sucks, and I just did that recently. And let me tell you how hard it was. It took me 15 minutes of reefing on that thing to get that cartridge out of the wall. I was
What'd
frustrated.
You say? You were reefering it?
Reefing it. You know what reefing is? Not referring.
I can only imagine what you guys are doing
I'm in Utah, and that's not legal.
Yeah, but not too. All the states around you has it. So
We already talked about that.
There you go.
Cheers.
All righty. So okay, let's go back. Any questions we have missed that we want to share here? That and again, guys, please, the floor is open for you. Any questions you have about tonight's material, or really anything hydronically related, we're here for you, and we'll stay on as long as you guys have questions, and we don't run out of answers. All right. Because
So
that's
one of the-
happened before.
yeah. So one of the questions that came up earlier, and I did answer it to everybody, but it was, what if you had PEX? And so when you were doing the flow and head loss calculations before,
Right.
the flow calculation still remains the same. Your head calculations, though, find the charts. Your manufacturers are going to put them out there. You find your flow that you have, find your pipe size, follow it down, and then multiply it by the length, because you don't have elbows. You don't have fittings thrown into the system typically.
Mhm.
Now, if it is a radiant floor system, you don't add up all the lengths of pipe that you have, just the longest if you have a manifold system in there. Okay, so you add up the gallons per minute per each loop that you have, that what you're supposed to, or when you do your head loss, your flow calculations for a room with radiant is, let's say you had a 10,000 BTU load in that room. Well, you've got 1 gallon a minute, but if you have 3 loops, it's 0.3. Don't put 1. Your numbers will start getting all crazy on you. You do 0.33 gallons per minute per loop, and then what's the longest loop that you have to figure that out.
Hey, Howard. Howard has a question.
Oh.
Asking about the VT2218, and does it display GPM? And the answer is, well, as of about 2 or 3 years ago, updates, yes. It actually gives you a fairly accurate, within about 5% flow rate. And so, yes, Howard, that 2218 does what you want it to do.
Earlier versions did not have the gallons per minute flow rate, but as the engineers worked on it some more, because they were off by about 15% in the flow calculations on the display, and then they were, and it's not a flow meter, it's just looking at it's an algorithm to figure it out, so it gets close. So it's not a flow meter built into the system itself, but we've got a lot better, so we threw it back in there.
Yeah, and you'll see that any variable speed circulator, doesn't matter who makes it, that has a display of GPM on it, it's at best an estimate. It really is. I can remember I was on a Facebook hydronics group, read some of the questions, and one guy who I know well, who's always the smartest person in every room he walks into, just ask him. He wanted to know what was wrong with the manifold, with the flow meters on his radiant manifold, because he had a variable speed circulator on it that had a GPM readout, and he thought something was wrong with the manifold, because he went to all those little flow meters and he added up what he saw as flow rates on like 12 different loops. He added them up and he said, it's not even close to what's on the circulator. And I had to say, dude, you're messing up on both ends. Number one, the circulator's probably 10, 15% high or low, plus or minus, because it's an estimate, mathematical estimate. And then on the flow meters, forget about it. Those things don't tell you. Those things are calibrated in, like that. They're not fine tuning devices, so it's like, wrong. We're asking the wrong questions here.
I was given an ECM circulator when they first came out many years ago in my old house. I wasn't even here at TACO yet, and somebody at the end of a trade show, somebody came up to me, hey Dave, I know you're putting radiant in your house, here, use this. And it was at the end of a trade show, and most of us that work trade shows, you want to take the least amount of stuff home. You want to try and give it all away. It had no box, it had no instructions. I even think it said on the side of the Circ Beta, but he gave it to me anyway, and I looked at it, and I'm going to put it in my house. So I put it in my house, and it operated on 0.0 gallons per minute for 4 years. It heated the house just fine. So
you had that happen too, didn't you, Rick?
Yep, 8 years at 0 gallons a minute.
Yeah,
it's the Blutarski grade point average, of circulators, right? 0.0.
So they get close. They give you an idea. They're not going to do the exactly what you need. Yes.
There we go. All right, here's a question from Thomas Flesher. If the baseboard is separated from the boiler by a load loss header, would this reduction in efficiency still happen when an oversized pump is used? Yes, absolutely. Maybe perhaps not to the same degree, depending upon if the boiler circulator is oversized as well. And we're going to get into Rick does a marvelous presentation on sizing the boiler circulator, and we're going to be getting into that in a few weeks. That is real critical here because it's so easy to oversize the boiler circulator, man. That's going to create, issues as well. So if both circulators are oversized, forget about it.
Forget about it.
Forget about it. Drop back 20 and punt is probably the best way to look at it. All right, very good. More questions, guys. All right, Anthony Tosco and his gang left. All right. Okay. Let me ask, the guys that are still on here. There's 90 of you. My goodness, they're still on. How are you liking online stuff like this? I'm sure you've gone to other stuff from other manufacturers and other training sessions. What we've noticed is that I think we've gotten a lot better at presenting in this kind of a format, but I've also noticed that the audience has gotten a whole lot better at learning this way. They're more comfortable with it. The level of interaction like this has actually gotten really good. So how are you guys finding programs? And not just this one, but I mean programs in general. Are you finding that this is a good way for you to learn? I mean, we all want to get back to face-to-face learning. Don't get us wrong, but we have the ability to reach larger and larger audiences in this kind of a way. So we're going to be doing both going forward once we can. But I'd like to know your feelings on these kinds of presentations and what kind of are they worth it? There's something hopefully you're finding this useful, but are others useful, etc. So give me some feedback on what you guys have. Jimmy DePalma says this is the best web training by far, not because I like you all, because it's true. Well, thank you, Jim. I appreciate that. It's really kind. Let's see. Like them to a point, Martin. That's a very interesting point. An interesting way of phrasing it. Explain that one because we want to make sure we do the best job for you guys as well. So that's all. That's pretty important. Okay. Gustavo says excellent. I pay more attention, make notes. Excellent. Easy to grab a beverage and just enjoy. Well, there you go.
Baby.
That's all right. What about circulator sizing? Okay, we'll get to. I want to get those guys. Just if there are any more comments there, that helps us a lot. That really does help us a lot. So in that flurry, we actually got a lot of really good questions here. Does TACO make a retrofit outdoor reset control for older cast iron boilers with perhaps a strap-on or immersion aquastat? Oh yes, the fuel miser. The fuel miser for cast iron boilers, it was just made for it. It's a great outdoor reset control. It protects the boiler from low return water temperatures. It's fantastic. On top of that, if you have an expandable SR or ZVC zone control, there's a little Molex plug inside that zone control. You could use the PC700 boiler outdoor reset control add-on, and it's really easy to put in. You simply plug it into that Molex plug on the ZVC or the SR, and simply move the dip switch inside from normal to reset, and that's all you do. You put the outdoor sensor on, a strap-on sensor on the boiler supply, and it takes over. And that's about as easy as it gets for boiler reset. So it depends on what you have for a control. Cool. All right. Okay, Larry says, I was going to mention, but you guys have the best online training around, informal and informative, not dry at all. No booze or hydronic pun intended. Thank you, Larry.
And I see a note here from Scott O'Neill, and he's saying it's easy. And I think that's also something else, that has to say about doing online training. So that it's easy to set up, easy to do. I'm assuming easy to attend. You don't have to drive somewhere. You don't have to explain to your wife or your girlfriend or wherever where you're at. So
Linda Ronstadt easy.
It's so easy to fall in love. Yeah. All right. Very good. Let's see a couple more. What about circulator sizing on where zones are on one circulator and an indirect is on another circulator? So you're talking about with zone valves. George. That's a good question. And I'm going to presume, and chime in if I understand your question correctly, sizing a circulator for a zone valve application. And then you also have a separate circulator for your indirect. Well, sizing a circulator for zone valves is very similar. What we're talking about, since it's one circulator for the whole house, the meaning one circulator has to supply all of the BTUs for the whole house. So instead of in our GPM equals BTUH divided by delta T times 500 formula, instead of using a single zone flow rate, just put in the whole house load. So say the whole house load is 83,000 BTUs, all right? So now it's GPM equals 83,000 divided by 10,000. That GPM is going to be 8.3 gallons per minute. So the circulator has to be sized for 8.3 gallons per minute. Now the question is, well, what's the head loss? Do I figure out the head loss for each zone and then add those all together? No, just pick the longest one, the worst case one. All right, it's a parallel piping system. So if the worst case zone is 5 feet ahead, then your circulator has to do 8 gallons a minute at 5 feet ahead. If you have, a 4 gallon a minute or 4 foot ahead, 3 foot ahead, and 5 foot ahead, you don't add them together and come up with 12 foot ahead, all right? You just pick the worst case head loss loop. So 8 gallons a minute, 5 foot ahead, you're good. You don't add head together in a parallel piping system, which is what we have with zone valves. Can you tell I'm Italian? Because I'm just,
I thought you were pawing at me or something.
So he was trying to make me look at him. I was trying not to look him in his direction. I was paying attention over here.
If you tied my hands, I couldn't talk or communicate, I don't think.
Hey, Clint's got one here. He's got a design firm, and it's helpful to hear from folks in the field. So he's looking at what we're doing on here and kind of taking it back to the firm, so to speak. But I'd like to throw this out for everyone. Now that we have circulators that do a fairly good job of estimating what the GPM and the pressure drop at that GPM is, I think we should all go, okay, if I'm going to do 25 jobs, I'm going to go out on those 25 jobs and I could see what I estimated or calculated in my pressure drop. And you go back and you see what it really is, because really no one knows what the pressure drop is. And John was saying this earlier, until we put a circulator on there. Once we put the circulator on there, it maps it out and it knows exactly what at a given GPM what the pressure drop is. What we should start do is making note of that and how much less it actually is than what we've actually been guessing at, right? So again, let's sharpen the pencil and get those numbers down there. Again, you go out to a job and people got fudge factor on fudge factor. John used to always say, John, it's amazing we don't all have diabetes.
That's right. There's so much fudge built into these things. It's amazing we're not all diabetic.
That's right. So
thank you for remembering that line. I love that line, but usually it goes over like,
Anyway, give credit where credit is due.
Thank you, sir. Jim DePalma says his favorite thing about these things is you don't have to wear pants to attend class. No, Jim, but it is a good idea.
Hey,
it's a really good idea.
Ask Jeffrey Tobin about that one.
No.
No.
Okay, everybody stand. Okay, here we go. No, I got pants on there.
Whoops.
That's it right there. Okay. Not wearing shoes, but I got pants. All righty. Is it possible to override the fuel miser after it shuts down the boiler when the outdoor temp reaches 70 degrees? Asked Phil May. Dave, you're our resident fuel miser expert.
Dave, what's up with that?
No, it has a built-in warm weather shutdown set at 70 degrees. Now it will run if you have an aquastat tied into the system with an indirect tank, but if you wanted heat on a if it's in warm weather shutdown, you're not going to get it. What you'll have to do is take the dial of the switch. So when you look at not the dial of the switch, the dial on the controller, it has numbers stating starting at 40 plus, 30, 20, 0 straight up at 12 o'clock noon, minus 10, minus 20, minus 30. And you're going to think it says minus 40, but no, that's when it says off. So you actually can turn it off if you have to take the controller apart to, the cover off, get inside, turn it to off, and then it just disregards the fuel miser altogether at that point. So.
And for those of you still on, I don't know if you saw it already, Dave put in, I believe that was you, Dave. You put in the link to download that copper tube handbook. It's a PDF, so you can download that if you really, really want to.
That's
It's
correct.
a
In
lot
the
of fun
chat section.
reading. I'll
Yep.
tell you what, it's a page turner. It's a page turner. I'll tell you that, man. Oh, nice. Thank you, Mr. House. Again, we weren't fishing for compliments, but it's nice to have them come on in. So you guys are the best on the training webinar circuit. Keep on hanging on. Yeah,
Aw, shucks.
Shucks, man. That's all right.
Shucks. Yeah.
And
You know,
Jeff House,
it's not working if you're having fun.
that's right. And Jeff House, I don't know if you guys, Jeff used to work for the TACO rep in Toronto and is kind of a hydronics legend in that part of Ontario. One of the handful of smartest people I know in terms of hydronics. It's just, if he doesn't know it, it's probably not important. So thank you, Jeff, for being a friend and helping us out and being here as well. So we gotta love that. And he's a new grandfather. So all right. Where do I send the check? Hey,
how many people here are grandpas?
No, I'm not.
Dave?
No,
Heck
you're
no.
not.
No, not at all.
No. So you're a grandfather. Jeffrey's a grandfather. Jim DePalma's a grandfather. Congratulations.
Yes,
Very
he
good.
is. Yep.
All right. So happy Grandfather's Day.
Yeah.
And number 2 is on the way. How about that? All right. Good for you. Good for you. Yep. Anthony Reichau is going to be a grandfather soon. All right. That's going to be great. He came over the house just a couple weeks ago or last week, I think. We went out to dinner. So it's good to see Anthony. Okay, from Howard, here we go. Replacing a 240,000 BTU boiler with a ModCon 175,000 BTU fire tube. Asked 2 weeks ago about upgrading the B&G 100 to a variable speed 2218, 100-year-old gravity system, 4-inch header, and a 3-inch trunk lines. I'm looking at a header under 2 at 130,000 EDR. Any thoughts? Oh, boy, that's a big one. I don't know if the VT22 is going to be big enough. We had this discussion. Didn't we talk about this last time?
No, why would it not be big enough? I'm all game. That pumps real hard to be small enough. It's only going to do 175,000 BTUs.
That's
what he's saying.
Okay,
Well,
and actually, we talked about this.
Only 130, so he only needs 13 gallons a minute with 2 foot ahead. He's only got 2 foot ahead in the system, so. Yeah.
Oh, okay. Yeah.
I would do it. Even if it doesn't work in Delta T, you could always just change it to speed 1, 2, 3, or 4.
Right.
There's a lot of things you could do with that pump. So I would give that a shot. I wouldn't have any problem with that. So.
Okay. All right. Yep. Cool. You guys are miles ahead of me on this one. Yeah, I think we remember talking about that, and maybe a way to go about this was continuous circulation that Anthony had suggested, and actually narrowing the delta T a little bit.
Yeah, try it at 20, see what happens.
Yeah.
I don't even think you need to try it at 20. It'll work just fine at 20.
Yeah. I think
so. We got a lot of those big old radiators weren't designed for a 20-degree delta on the systems. It was
they weren't.
Give me everything you got.
Yeah.
Let's go.
There you go. Yeah, because again, all gravity system was continuous circulation, right? It was very gentle, continuous circulation. So yeah, you can actually go. I would think continuous circulation at a wider delta T would probably be fine. Yeah. Because once you're up, you're up. Yep. And once you're down, you're down.
It's up and down.
And even when you're halfway up, you're neither up nor down. Those are all conjunctions. I don't know if you picked up on that, right?
Just like in and out.
I'm grinning away.
Yeah. Neither nor, either or. Not this, but that. Out of the frying pan and into the fire.
Into the fire.
That's right.
So at 13 gallons a minute and 2 foot ahead in the system, that the VT 2218 is going to be running at about 60% speed.
Oh, perfect.
You got, and it's on the bottom end of the curve, so it's closer to the flow chart on the x-axis than it is on the y-axis, and about 60% speed. So you've got plenty of room to play around with on that circ.
Yeah. And then you can see, try narrowing the delta T, try widening it, see what works best for you. That's cool.
I just want to, let's see here. Whoops.
There's the fuel miser.
Okay, that was a fuel miser, but then I wanted to pull up this curve. Are we looking at the curve?
Yep.
Okay, just making sure. So we take a look at that, 13 gallons a minute, 2 foot ahead, sitting right there. Okay, so you can see the mouse though, right?
Yep. Mm-hmm.
Yeah. So yeah, it's you got plenty of room to work with there, Howard. Definitely.
Very cool. Very cool. Yeah, there's so many just really interesting things that we all learn. I mean, that's one of the great things about this. We all kind of learn together. So that's awesome. That is awesome. And yeah, that's one thing to remember too about the VT2218, something we don't talk about very much because sometimes too many features gets confusing, but you can take it out of delta T mode and it's now a 4-speed pump. And I can remember doing a training class. It was in Toronto with Jeff House many years ago. And I was asking the guys, why do you use 3-speed pumps? Because I was curious and got a lot of different answers. But the best answer I got, why do you use the 3-speed pump? And the guy looked at me and says, because you don't make any 4-speeds. You made a 4-speed, I'd use that. And I said, all right, well, we got one. We got one. That VT22 could be a four fixed speeds. It could also be a set point pump where you just use one sensor and the pump will vary its speed to maintain a fixed temperature in anything, whatever you want to try to maintain a fixed temperature in, which is kind of cool.
Mixing. Yep.
Yep.
Yeah, I've used it on some small snowmelts like that.
Mm-hmm. You're trying to maintain a temperature on the outlet side of a heat exchanger?
Correct, right, without having to put in a mixing valve. So if
Cool.
you don't have any mixing going out onto the, making a small snow melt, let's say it's a small patio or walkway coming in, or steps coming into the house, you don't want to get too crazy with your controls or your mixing. You throw a heat exchanger on so you don't have to fill the boiler with antifreeze, and you put the VT pump on the boiler side, the fixed speed pump on the snowmelt side, but the temperature sensor from the VT goes onto the snowmelt side of the heat exchanger.
Yep.
It'll
Right.
ramp up and down as the load changes. It's a really, really neat way to get a simple small snowmelt system up and running.
Yeah, and you maintain just a fixed temperature on the snowmelt side, and that the pump will ramp up and down to do that. Yeah, that is pretty cool.
As the snow starts to get heavier, the pump is going to ramp up because the delta T is changing, and as you're going through the mixing through your heat exchanger, the temperature's changing. It works wicked cool. If I could steal that from you, John.
Yeah, that's wicked awesome. It's okay.
Okay.
Air handler, air temperature downstream of an air handler.
Mm-hmm. Yeah, you can put the sensor in the airstream of an air handler. Pump will speed up and slow down to maintain that temperature. Another great application for the VT2218. And then it also can be put into chilled water mode. Just it works backwards.
But just remember, if you use it in an air handler mode, you have to have a switch to turn the pump on and off because it has a minimum speed.
Right.
And I do remember a couple of guys dropping it into systems like that didn't have thermostats. It was like in a complex with a bunch of stores, little mini mall, so to speak, and one central heating plant, individual air handlers. They didn't have thermostats set up in all the spaces, so they just put the VT in there, put it on one temperature sensing, and all of a sudden the next day they walked in, it's 90 degrees in the hair salon. So because they had no thermostat to shut, it was on the bottom end of the curve. It was May. There was still a heat call. So yeah, you need to have a switch to shut it off. So.
Indeed. Is that a Toto shirt there, Rick?
It is.
Toto,
1978.
What a great band.
Oh, top notch.
Rosanna.
Anyway. Now, well, that's the stuff that makes the radio, just like always, is not really their best stuff.
Yeah.
They got Grammys for it, but if you really want to get into Toto, you want to see some of the later stuff where that's avant-garde. Nothing ever made the radio, but shows their true musicianship. They're wonderful, all of them. All what do they call them? They're A picks for people, say somebody like, well, Boss Gags
Mm-hmm.
wants really good musicians to play for him on albums. Who do they hire? Toto.
Toto, right.
Yeah. So, just stuff like that. Yeah. Anyway,
Yeah.
they're
I'll
one
tell
of
So
my
you said
faves.
1978. Is that shirt from 1978? Because
No.
I'm sure there's some people on
Nope.
here younger than that shirt then. Okay.
Nope. No. The shirt. Oops.
You wear it once
Sorry.
a year?
It's just up in the drawer. I chose it over a Takeo shirt. Toto and Takeo.
Toto and Takeo.
Four-
Close enough.
yeah,
I
four
was
letters,
walking the
close enough.
dogs today, and my playlist came up just several tunes from what I consider maybe the most underrated rock, really good rock band of the early to mid 70s. I mean, just incredibly underrated. They had some hits. Everybody knows them, but you really get into like the back end songs, and there's just some amazing, great stuff. Who do you think I'm
And
talking about?
I don't know. Talk to me. I might
Mm,
want to go buy it if I don't
yeah.
have it already.
They had three guys.
Oh, Three Dog Night.
Nope, not Three
Oh,
Dog Night.
Rush.
Nope.
Grand Funk Railroad.
Bada bing, there you go. Mark, Don, and Mel. Grand Funk Railroad was one of the coolest, awesomest bands that just is never, no one ever says, my favorite band's Grand Funk Railroad. Nobody ever says that, but
No.
damn, they're good.
They were good three-piece power trio, babe.
Yep.
They were great.
Yep.
They had a live album, a double album live set that was from like 74, 73 or something like that. And it had a song called Into the Sun. Look it up.
Into the Sun. I will.
Into the Sun. Yeah.
Yep. I mean, I've seen some of the YouTube stuff of some of their old concerts, and they were just events. I mean, these guys would go nuts, and just to put out for three guys, they were powerful, man. It was really good. It was really good. They were. Jim De Palma throws out Cream, and Cream was a '60s thing. They didn't go into the '70s. They were '60s, and they were the original power trio. But I'm telling you, Grand Funk Railroad just in terms of everything. What a great band. What a great band. And Richard Ravita, he gets it. All right. Yep. Good for you. All righty. We actually have a question here. Another one from Howard. Great, man. Want to minimize return temp to maximize condensation for maximum efficiency. Navion NFC 175 with outdoor reset modulates from 18,000 to 140,000. My plan, have it turn on in the fall and not cycle until spring. One long cycle. I like. Very good.
Modulate the world.
Yeah.
Modulate the world, baby. Gotta love it. Gotta love it. How many cycles? Go back and check the log. How many cycles? One.
Yeah.
That's good. That is good. There was a guy who ended up at a Takeo training that he got on the wrong bus. He was wanting to go to Tyco.
Tyco. Yes.
Yep. Yeah. We there's a company, and I don't know what do they do.
They
a company
do
in Rhode
Fire
Island.
suppression.
Fire handlers.
They were doing fire suppression design.
Yeah.
Sprinkler heads and pipe designs and stuff. So
Yeah.
a lot of plumbers still in the same hotel.
Yep.
Yeah.
And Tyco was one of their plants was around the corner from us in Rhode Island. So we've had it more than once. Actually, one of the last classes, we had two guys get on the Tyco bus, and two of their guys got on the Takeo bus.
Wow.
So we had to
Couple of
swap.
phone calls
Flip-flop.
between the two, and we said, "Oh, by the way, we got a cab already heading to you guys. So when that cab gets there and your guys get out, have those two guys standing in your lobby, send them over to Takeo."
Yeah, I think one of the guys was from the South too, and he said, and when he went downstairs, he said, I want to get on the Tyco bus. And
Tyco.
Tyco, it was kind of the same thing, and he said, got on that
Yeah.
one.
Yeah.
Oh yeah, it's interesting, and you got a thick Rhode Island accent too. You say it sounds the same, so it's kind of funny.
Hey,
Martin's off to shovel snow. Where are you, Martin? Snow?
Martin.
Not winter yet, man. You must be up Michigan or Minnesota. Where you at, Martin?
Yeah, I saw Minnesota got about 8-9 inches.
Minnesota got a
yesterday.
bunch.
Yeah.
Yeah. Western Canada. Oh my God.
Don't worry, man. It'll melt in the spring. Don't worry about it.
Calgary. Don't worry about it. Yeah. You got a snow melt. You've got nature's snow melt, man. Just let it melt, baby.
Hey, for Howard
comes
there,
every year.
I think Howard is actually drilling in on what he would like to do. So Howard, on your question in regards to that Navion NFC 175, hey, put a VT 2218 on there. And you know, the same issue you'll see is the same problem I have. You can't go any lower than low. So there's times where you won't get your 20 or 30, or like I got mine on my house set at a 30. Well, there's, you know, again, once it gets to low, it can't go any lower than low. So I might only get a 20, or I might get a 15, but it's absolutely the lowest you're ever going to see if you were to compare it with a fixed speed pump. So at least, you know, if you don't have feedback coming from the boiler manufacturer to the circulator, like 0 to 10 or pulse width modulation or something like that, then the next best thing is to use, as long as it's sized right, is to use one of our 2218s, and it works really good. Howard, I'd give that a shot in a heartbeat.
Very good. And Richard says home runs at 1 gallon a minute with the 2218 and drill down on the delta starting at 30. Good luck.
Yeah.
And Richard's another one of those guys. I don't know if you guys know Richard. Just a sharp, smart guy, man. And you know, Richard, I look at you and I see a guy playing, you know, three-dimensional Klingon chess, while the rest of the world's playing Candyland. All right, that's Richard McGrath. I don't know if the rest of you guys know that. That's Richard McGrath right there. Just you know, playing a game, as Bobby Jones said about Jack Nicklaus. He plays a game with which I am not familiar. And and I mean that as a compliment.
Yeah, he looks at it from a different angle, definitely. So Rich is, you know, and you know, Rich has the opportunity that we don't get any longer, as in he still gets to install it after he designs it, and then also teaches his company and the rest of his guys at his company, you know, how to do it like we do. So, which is really cool, you know. So, yep, Good to see you, brother, man. We had a nice conversation today. Working on it, brother.
Very good, very good. All righty, folks. Any more questions? Keep them coming. Like I said, well, there's 50 of you still out there, so we'll stay.
Well, I'm going to extend upon what Rich was saying here, and I know he was leaning that towards Howard. He was saying, you know, get a manifold, like a radiant manifold, 1 gallon a minute. You can do that, you know, with some PEX on there and go out to those radiators and stretch out that delta T to 30 degrees with the VT 2218. So no reason why you can't run PEX out to each one of those radiators now, and you know, you might change that head calculations a little bit on what we were talking about, because you said before you had about 2 foot of head, but that's based on the old gravity size pipe. If you were to change it to using PEX, use a radiant manifold, keep it high temp, and maybe work out a 30-degree delta, that can really work out advantageous to you and get that boiler to condense as much as it can.
Very good, very good. All right, Jimmy DePalma's left the building. All right, Richard says get the temps as low as you can and play from there. Howard Leggett says BNG 100, my delta T estimated 10 at 22 gallons a minute, no callback mode. I think it will kill the boiler. Yeah, you're probably right. You're probably right. You can do better. You obviously can do better at a 10 than a 10, clearly. And I think what the guys have suggested is an outstanding way to go about it. Cool.
Beauty, eh?
All right. Any more? Say what? My phone be dinging. I've got a couple pictures from, again, another picture from Anthony of his guys. How does he have this set up here?
Well, you got to share now. I can't see them.
Well, I'm just looking at it right here. There you go.
Oh, okay.
Yeah, I don't know if you can see that. There's the boys.
Oh, it's in the shop. All right. Okay.
He's in the shop. He got a little projector set up, and they're watching the show.
Like the guys are wearing hoodies and jackets. Anthony, turn some heat on in the shop. Come on, man.
I know, really. Come on, man. Nobody likes a cheap boss, Anthony. Let's go. Very good, very good. All righty. Well, Richard's got another comment. With the home runs, the system flow should always be higher than the boiler flow, which is good for the system. Absolutely, absolutely.
Yeah.
All right. I'm just looking around at different toys I have here. Now, we all know what this is, right?
Yeah. Yep.
That is a Taco 4900 Dirt Mag separator. And you may be looking at it like this and thinking, well, that's the 4900 air separator. No, no, no. This is its downward facing brother, the dirt
Downward
mag
facing
separator.
dog.
Downward facing dog. Yes, there we go. All right, the downward facing dog. Inside, as you can see, let's make it there. There you go. You can see the pawl rings, just like in the 4900 air separator, but here they're not for the coalescence effect to remove bubbles. Here it's collision. It's a collision medium to get dirt and magnetic crap to separate from the flow as the velocity slows down. This guy right here is a very, believe it or not, an incredibly powerful magnet. All right, that's over, how many was it? 13,000 Gauss. This is a high Gauss magnet, that will, you slap that on and it will attract and keep that crap in the lower portion of the section to clean out the system. When you need to blow it down or drain it out, you turn off the circulator, you remove the magnet, open this thing, and all that crap will blow right out. Russell asked, where would you use something like this? These are always on the return side of the system before they go back into the boiler, whether it's a modulating condensing boiler or really even a cast iron boiler. You want to try and protect the boiler and keep this crappy stuff from getting to the boiler, which can cause you all kinds of headaches.
Yep, go ahead. Sorry.
No, go ahead. You were
I was
ready.
going to say, because a lot of the older cast iron boilers have what we call designed into them a mud drum. You know, the mud legs, it would collect all the stuff because you had this big void, and as the velocity of the water dropped and it entered the cast iron, everything would just settle out. We don't have that much anymore. So everything stays in solution and starts still sending around throughout the house, you know, through the building itself. So if you start looking at, you know, pump seals are failing, check valves are getting stuck, you know, you're replacing components way too early, it looks like it might be a water quality issue.
Right, and that stuff can build up in the passageways of boiler heat exchangers and collect there and kind of sludge up, and that can cause, you know, that slows down the heat transfer from flame to water. That creates stress points, that causes heat exchangers to fail. And here's the thing, boiler manufacturers are catching on to this. We're seeing more and more boiler manufacturers saying, hey, you know what? You didn't treat the water like we told you to. That was this thing failed because of a crud buildup. Guess what? The warrant, we're going to void the warranty here, pal. You know, then you go ahead and have that conversation with the customer. Good luck to you. It's uncomfortable, but that's the reality of the situation. So water treatment, water quality is very, very critical. Now, over the summer, we had a fantastic presentation. You guys remember this one with Patrick S is his last name, ESS, from Mondale and Associates on water treatment for boiler systems. If you go to our YouTube page or even go to our website and look at our training, our library of webinars, it was over the summer. It was a Takeo After Dark over the summer, and Patrick did a phenomenal presentation. Okay, we were on for almost 2.5 hours. You know, it was a 1-hour presentation, and guys just kept asking questions about water quality, water treatment. What does this mean? How do they do this? All these fantastic questions. And Patrick just, I mean, he was on fire, man. He was absolutely on fire. So if you want to learn about water treatment and water quality, that's a great place to start. Really great place to start. Guy knows his stuff.
I'm going to show a couple of slides I put together real fast. Oh, I'm still the presenter. Look at that. So just to show you a couple of things to think about when you're looking at water quality, do you think you have an issue or not? Because a lot of times we don't pay attention to it, right? But if you see your pump seals, you know, yeah, you're going to see that not in a 00 series, but you're going to see that in your 3-piece systems, right? You find your IFCs, you know, circulators getting jammed up like this one here. That's a lot of jamming. Zone valves not closing. All right, is going to cause that also, right? Low water cutoffs, if they seem to be tripping prematurely, it's getting buildup on there, right? And your heat exchangers. I mean, these are all pictures from job sites. You know, all these things are taken out of here. Some of them may be extremes when you start thinking about it, but it might need to be considered water quality. You know, you might need to put stuff in there in order to treat it, some chemicals, but also trying to get that stuff out of there. That's what the dirt separators are going to do for you, to try to grab that out. There's a lot of different sizes that we offer them all. And this black part down here at the bottom is the magnets. And when John said before, 13,000 Gauss, if anybody has touched one before, you guys got them right there. Pull the magnets out, right? You showed them in the camera before. And if you've heard other conversations out there of the Gauss of the magnetic strength, I know I've been to plenty of trade shows. Guys come walking over to our booth, the Takeo booth, with their big magnet wand.
Oh, baby, look at that.
Right?
Babe.
They walk up to the circulator. Yeah. It's a new bracelet too. Yeah. You pick up a circulator with the magnet. So let me talk about what Gauss is for a second, in case you're curious. As anybody that's coming out with a magnetic dirt separator, we start talking about the Gauss to try to separate it from each other. So let's just run the numbers for a second. So we say ours is 13,000 Gauss with these little watch batteries. The Fernox TF1, great equipment, great piece of equipment. It's got this really strong magnet that picks up a circulator. The 80 MagnaClean, same thing. This big magnet, it's like 8 inches long. Pick up a circulator with it. The Caleffi Dirt Mag 2600. What is Gauss? Just so we're all on the same playing field, has nothing to do with magnetic strength. It has to do with magnetic field strength. All right, it's what they call the flux density. And every time I say the word flux density in a training class, everybody goes back to thinking, Back to the Future. Yeah, the flux capacitor. Exactly.
1.21 gigawatts, right?
That's right. So you see this a U magnet here. The flux density there is quite dense because the north and south poles are opposite of each other. So the field strength is stronger. When you look at a bar magnet, the reason why you see the Fernox and the 80 at 9 and 11,000, and that we're higher, which is crazy because they can pick up a circulator with their magnet, is because they have a bar magnet in there. So they have a really strong bar magnet to try to get these lines closer together. But when you do the north and south poles opposite of each other, that's when the density gets stronger. So just so you have an idea of what it all means, when you are out there shopping for something, take a look at it and obviously make your own decisions. It's going to work for your applications, for your projects and your job sites. So that's all I wanted to say about that.
I want to add to that, Dave. Dave's got a good point there, but our point is really not, that our magnets do that good a job. It's more about that whole colliding of the particulate and the barrel size and getting the stuff to drop out, and then we pull the magnet, pulls it in there. So it's more about how well a job we do with, particulate dropping out of suspension, and then the magnet just merely holds on to it once we get it out of there. We do a really good job with those Paul rings, and nobody else has that technology.
Right.
So in North America. So
there you go. Oh, and Richard McGrath found the Wikipedia page for Carl Friedrich Gauss. That's right. When we had to learn about this stuff and put the presentation together, I went to old Carl Friedrich's Wikipedia page, learned all about him. So the Wikipedia is, you can get lost in Wikipedia. I don't know if you guys ever done that. Just you start chasing, you look up one thing and then you start chasing into all these different rabbit holes of 6 degrees of separation on, how does, Amy Adams relate to Carl Friedrich Gauss? There's a connection there. You just have to find it.
And you forget why you went to the first place, right?
Exactly. But it's great for research. It's not always 100% accurate, but it sure makes for interesting reading.
How many people give them money?
I have, for as much as I use Wikipedia, I've never donated.
Anybody out there ever actually give them $20?
It's probably worth doing for as much as I use Wikipedia. Yeah.
Amen.
But then again, I also have to take half the stuff with a grain of salt because anybody can edit it.
Yeah.
So that becomes a challenge too. So if you're reading something, it's like, well, is that really true or not? I'm not sure.
Just like everything on the web.
I have to go find a couple of other websites to try to corroborate with the Wikipedia page just to make sure all right, more than one person saying the same thing at the same time. So
Yeah. I mean, I saw a great quote on the internet the other day that really put everything into perspective. And it was pretty simple. It says, don't believe everything you read on the internet from Abraham Lincoln. So yeah, that puts it into perspective, does not? Yeah. Scott Williams has a question. Could you use the Taco Dirt Mag on a well system? No, it's not lead-free brass. It's designed for a closed-loop hydronic system, so it does not have NSF approval. You wouldn't be able to do that.
yeah,
You
looking
could
more
if
for
you
a
want your
filter.
kids to look a little funny.
And it worked for our parents.
Yeah, I remember chewing on the actual windowsill with lead-filled paint, pulling things off. And that's why I am what I am.
It explains much. It explains much. Yeah, last question. Is there a minimum velocity flow rate for the 4900 air separators when they lose their effectiveness? No.
Minimum.
The whole point is you want velocity to get really, really low in an air separator, because the lower the velocity gets, the more dissolved gases want to come out of solution. And where do we want them to come out of solution? In the air separator. So there's no minimum velocity there. Yep. So as Richard says, the slower the better, because that's the situation where dissolved gases come out of solution. So, and that's why our pipe sizing guidelines that we discussed last week were based on minimum and maximum velocities, a minimum of 2 feet per second, maximum of around 4. When you start to get below 2 feet per second, velocities slow down, dissolved gases come out of solution, and you start to have air issues. An air separator starts its life as a big open space in the piping where the velocity does slow down. That's what we want it to do. So there's no minimum there. And Richard says that's why buffer tanks are the best air separators, because velocity can slow to a crawl right in there. Yeah, that's why a good buffer tank should definitely have an air vent up on the top. It's all good. It's all good. All right, we still got 40 of you guys out there. This is awesome. I love this. This is my favorite part. I don't know about you guys. This is my favorite part. There's no pressure. A lot of fun interaction. Richard saying good night, so you spoiled my evening. You're harshing my mellow, Richard, man, by signing off.
From one Richard to another.
There you go. Good night, Richard. Thank you for everything tonight. Appreciate it.
Yeah, bro. We'll talk tomorrow, I'm sure.
There you go. But yeah, we still got about 40, but this tends to be one of my favorite parts of the presentation, because I think a lot of you guys are just listening to see what we're going to do next.
We're waiting on you.
And we're waiting on you all. That's right. We're waiting on you. So we want to know what you guys want and what questions you might have. And we do our best to answer. If we don't know, we don't know.
Yeah, we'll tell you. We'll tell you, man.
There you go. There you go. Now, what's that thing on the wall behind you there, Rick? Above the 0034E plus. Look like a plaque or something on the wall.
A poster?
Right over the 0034.
That's an Arbor Crest Wine Cellars poster. When we go up into Washington State, they got a great little winery there that we have frequented, and so we got a memorabilia.
Very nice. Very nice.
It's not. I didn't put it on there so everybody could look at it on Taco after dark. It's just on my wall.
Does it make you happy? Yeah.
It makes me happy.
That's what you put stuff on the walls for, to make you happy. That's right.
Those fond memories that you hold on to.
Indeed, indeed. Now I'm sitting here in my office, which, as you can see, is dark.
Okay. Yeah, darkness.
I got the lights turned off because the light's right behind me, and it would look like a big halo over my balding head. So.
Ooh. When are you gonna go like Dave and I? Put your head down like this.
I'm just gonna let nature take its course. Okay. I mean,
all right. Okay.
I still enjoy the whole the process of shampooing. So I'm gonna hang on.
Believe it or not.
And spending the money on it and stuff too, right? Yeah.
That's it, man.
That one little drop that goes in the middle of your palm, right?
Yeah, I buy the cheapest shampoo I can find too. I'm not into that designer stuff, which is probably why this is happening faster than we want. But
use a bar of soap.
No, I'm not crude.
Oh, okay. I'm crude, I guess.
I'm cheap. I'm not crude.
See you, Phil May. Take care.
Yep, so Russell was asking, where does he find some of the takeaway after dark? So if you had signed up for all of them, you would have gotten an email the day after for a link to it. And we have to actually upload them to the Takeo website. They haven't been the sequel, the full session hasn't been uploaded to the website just yet. Any of our sessions, the first session in the spring has been, which still kind of followed the same topics. So if you wanted to go find Takeo After Dark session 2 from the spring, same topic that we used. So you could find it there. But we do need to get the sequel or the fall session uploaded onto our website and or also our YouTube page. So I know we're a little behind on that. So I apologize for that. So there's no reason for you to miss any.
There you go. Well, hang on there, Russell. I think I can do something here for you.
Oh yeah, you got the link for those. Yes.
I
Excuse me
can
one moment.
I can do this. Just give me a second. I'll go to the video library. All right. And what I'm going to do is I'm just going to post this link to the second part so you can watch it. Where are we? Takeo After Dark, part 2. There it is. Do 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 do. Do do do.
Where you putting
go, Russell.
You sending it to him or you putting it
I'm
on the
sending it to
chat?
him, and then I'm going to put it out there for everybody too.
Oh, okay. Reply to all.
Yeah. There you go. There's the link right there for you.
All right.
And
That's
can,
it too.
Yep, it's episode 2. You just what you'll do is you go to our GoToWebinar page and you'll just you'll log in, just fill out your information and then you can go in and watch it. And it was one of my personal favorites. Heat emitters just always get me going. I don't know why. It's one of my favorite things, man. One of my favorite things. All righty. Where did Rick go again? He said, I looked up and he's gone.
I don't know what he just muted and turned the camera off. So
yes, man, to go do something. All right.
Yeah. Well, get rid of some Mayo Rita.
There we go.
Some used Mayo Rita. Yes.
Any more questions?
Yeah, I don't see anything coming in.
If we sign off before Rick gets back, man, he's going to be very upset. Where did everybody go, man?
He's still with us. I got him.
Oh, there you go. We got the Lorax.
Yes.
Yep. We determined in our spring session that Rick Mayo is in fact the Lorax. There he is.
My ears are burning.
Rick Mayo is in fact the Lorax. There's just there's no disputing it. He's one and the same. He's one and the same. Because Rick, the Lorax is your spirit animal. When I think of the Lorax, I can't think of a better representation for what you are and who you are and what you represent. Because I always that quote of the Lorax, unless someone like you cares an awful lot, things are not going to change. They're not. That's something you would say. And that's kind of, I know that's how you live your life too. So
I wish I had have said it, but
I wish you know what, you haven't said it, you've lived it. And that's one thing I admire about you.
Oh, that's even better.
Yeah, it's pretty good, huh?
Yeah.
I got nothing I say about you today, Dave, but other than no, you know what, for you people who are still left here, there's still 33 of you there. I want Dave to show you that plaque behind him.
Yeah.
This is impressive.
Oh, you mean Dr. Evil?
No, the plaque. You know what I'm talking about.
Placard.
This Dave, my friend here, is an award-winning industry trainer. This is a big deal. Keeps it right by his booze, which is good.
There you go.
There you go.
You should hold my Dan Hollahan books up too.
Yeah, if you're gonna hold up Dan Hollahan books, it's good to hold them up with Jameson. There you go.
That's right. That's right. So this is the Dan Hollahan Instructor of the Year Award from OESP, presented last year. Or actually, I'm sorry, this year. This past May.
That's right.
Yeah.
That's
the past
2020.
year.
That's 2020. And OESP stands for our folks who may not know.
Oil and Energy Service Professionals.
That's right. Yeah. A major organization in the Northeast part of the country for traditional oil dealers and the businesses that they've morphed into. Been together for decades, and Dave was named Trainer of the Year by that organization. And I can't think of a more deserving person for that award. Bursting with pride over both of these gentlemen, I'll tell you what.
Oh, thank you. It's all for you, brother.
Well, Hey, that's all right. Just checks in the mail. That's all I care about. All
Keep it
righty.
coming.
Well, I think with that, I think we should probably sign off. The questions have slowed down. We're down to 35 of you out there. So last call for anything else. Otherwise, we're going to flip all the cards and say goodnight until next Wednesday for
All right.
episode 5 of Takeo
Episode
After
5. What
Dark.
is episode 5? What are we doing in
Episode 5, we're going to start the conversation on variable speed ECM technology.
There we go.
We're going to
Okay.
start that conversation and we're going to finish it the week after. So next week is myth busting.
Good.
So we know what the real story is, not the fancy stories that people who really don't understand what these things do keep telling us.
I guess we'll be hanging out with this panel next week, huh?
Oh yes, definitely.
Okay.
Definitely. Most definitely.
All right. And then I'll leave it up there. I don't have to take it down.
Terrific. All right, folks. Hey, thank you all. Very much appreciate the gift of your time this evening. And on behalf of Dave and Rick, just want to say thank you. And we will see you next week. Same bad time.
Same bat channel.
Bat channel.
Same bad channel. All right. Take care, y'all. Be good.